Okay, so welcome to the first tutorial of this series. Uh, in this tutorial, we're going to be learning how to use the thermodynamic tables, which are shown here. And this is perhaps the most important tutorial because the concepts you learn in this tutorial will be applied throughout. So be sure to pay a lot of attention to this tutorial because it is quite important, right? So let us begin. So before we start doing questions in this tutorial, what I would like you to teach, I would like to teach you is if we have certain properties of the substance like temperature, specific volume, pressure, specific internal energy, specific enthalpy, specific entropy, then how do we identify its phase? That is, if we have certain properties of the material, then how do we identify where on this line, just a second, where on this line does the material lie? So let's start with case 1. We are given pressure plus temperature. That is, we know the pressure and temperature. So method 1 is to calculate T sat at the given pressure from table. Try to recall T sat was the boiling point with respect to what I'm telling you. T sat was the boiling point at P sat, right? So T sat can also be said to be this temperature. That is the temp at which substance is a saturated mixture. So this point is known as T sat. So as we will see in the table, in the table, if we see table B12, B.1.2, we can see at 1 kilopascal, T sat is 6.98 degrees Celsius. At 1.5 kilopascals, T sat is 13.03. Let me see if I can annotate on this. I cannot. So you have to follow along with me with your table open, right? Because that is the way you will learn how to use it. So you have various pressure entries and you have various corresponding saturation temperatures. Intuitively, what this means is that if your pressure is that value, then the corresponding temperature is the temperature at which your water will start boiling. Right. So once we have that, let us draw our table. This table will be drawn again and again and again and again and again. So it's very important that you know exactly what is going on in this table. So this is your P equals constant. Constant as in you know the pressure and we are using the pressure here, right? This is a TV diagram. We know the pressure. And at this pressure, we have found out the corresponding T sat from table, right? So what is the data that we have been given? We have been given pressure, temperature. Pressure data we have used to find the Tsat, and now the only thing remaining is the temperature. There can be two outcomes here. T can be greater than Tsat, or T can be less than Tsat, or T can also be equal to Tsat, in which case it will be lying here, but we'll see that in the end. So in case 1, where T is greater than Tsat, that means suppose this is your T1 greater than Tsat. This is T1. We draw a line, we draw a line, we draw a line. And we see that these two lines intersect at this point. We also know that this is the superheated line. Try and recall from the previous lectures, superheated line. That means it must be a superheated vapor. I hope you understood how we got this, because it is a bit complicated at first. Let's have a look at it once again. We were given pressure and temperature. We used pressure to identify Tsat. Then we saw that a given temperature was greater than Tsat. So it must have been lying somewhere here. But if we draw a line from that temperature, we see that the material can only lie somewhere on the superheated line. That means the phase of the substance must be superheated vapor. Got it? Now this is case 2, where a T is less than Tsat. This is T2 and T2 less than Tsat. Again, if we do the same horizontal line method, we see that the temperature line and the phase line intersect at this point. And we know that this is the subcooled line or compressed line. So that means the substance is subcooled or compressed liquid, which implies we get compressed liquid. And our final case, if T equal to Tsat, then it will lie on this line. It can lie anywhere on this line, here, 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 anywhere. But it will definitely lie on this line. So it implies it is a mixture or a saturated mixture, we say. Don't say mixture, say saturated mixture. So what we did was essentially use various parts of the graph and see at corresponding temperatures which part of the graph the substance can possibly lie in, right? If temperature was greater, then the two lines can only intersect in the superheated vapor line. So that means the substance must be lying on the superheated line. So it must be a superheated vapor. And then we applied the similar approach to the subcooled substance. Now we can do the other thing also. This is case 1 ka method 2. Calculate Psat at given T. Because again, we have been given both pressure and temperature. So here we will be drawing PV diagram. Because given T means we take T equals to constant, right? And this was the constant pressure line here. So we must draw a constant temperature line, not in a TV diagram, but in a PV diagram, because in TV diagram, a constant temperature line is just a horizontal line, right? So it will not do anything for us. So again, let us draw a PV diagram. Remember, it is inverted TV diagram. However, the regions do remain the same. So this is our constant temperature line. Again, we can have two cases. P can be greater than Psat or P can be less than Psat. So if we see at suppose 100 degrees Celsius, a saturation pressure for water is 101.3 kilopascals in table B11, right? And at 105 degrees Celsius, it is 120.8 kilopascals, and so on and so forth, right? So now, similar to how we compared the values of temperature in the above graph, if P is greater than Psat, so let us say this is our P1, and clearly P is greater than Psat, right? Because where will the Psat point lie? It will lie somewhere here. And again we see that it intersects here. Now this is the subcooled line. This is not the compressed line. So this is not the superheated line. Wait, let me just confirm that. See, after all this time, I also get confused sometimes. Yeah, so this is the subcooled line. So if P is greater than Psat, we can see that the intersection is on the subcooled line. Similarly, if P is if P is less than Psat, then the intersection is on the superheated line. So P greater than Psat implies subcooled or compressed. Both terms are used, and P less than Psat implies superheated. Try not to remember any of this. Don't remember this. Every time just draw like a mini graph to the side somewhere and try to visualize what will happen in that graph. That is the short method, because you will always doubt your memory, but you will never doubt what you draw on the spot, right? And again, if P equal to Psat, that means it will lie somewhere on this line, anywhere on this line, and it will be a saturated mixture. Later on, we'll also learn how to find where exactly on this line our substance is lying through a what do you call it? A variable, yes, a variable known as dryness fraction. Okay, so now this was case 1 when we know pressure and temperature. However, this is not often the case, right? So let us jump to case 2, where we are given P and specific volume or T and specific volume. Again, we will draw our TV diagram and our PV diagram. I'm telling you again and again, this is perhaps the singular most important diagram. TV. I'm just going to divide up our regions again. And PV. Remember, it is inverted. Right. This is our, what do you call it? Compressed or subcooled region. This is a mixed region, saturated mixture region, and this is a superheated region. Similarly, this is our subcooled region. This is our mixed saturated mixture region, and this is a superheated region. Alright, now I'm gonna teach you something important. Look at these points, the points at which the liquid is in saturated is a saturated liquid and a saturated vapor respectively. They have a value corresponding on the t axis, which we called as tsat, but they also have two different values corresponding on the v axis, specific volume axis. So the saturated liquid point is called vf, and the saturated vapor point is called vg. Similarly, over here, as over here it is a saturated liquid, the corresponding specific volume must be Vf, and here, as it is a saturated vapor, the corresponding volume must be Vg. Now let us say we have some given value of V. Let us refer to our table and go to the 25 degrees Celsius just as an example. 25 degrees Celsius in B1.1. We can see the saturated liquid under Vf is given. So the value of Vf at 25 degrees Celsius for water has been given. It is 0.001003. Let us write that down. Vf is 0.001003. Similarly, Vg is also given. The value is 43.3593. Now, we will be able to identify where our given volume is lying. Let us denote by V given. Example, if V given is less than Vf, that means it is lying somewhere over here in this region, and we know that it is a subcooled region, so that means our substance is subcooled. If our V is lying between Vf and Vg, it is lying somewhere in this region, and we know that this is the saturated mixture region, so that means our substance is also a saturated mixture. And lastly, if our V given is greater than Vg, that means it is lying somewhere in this region, which means it is a superheated vapor. Right? If you don't understand that, we're going to do it one more time, but on the PV diagram, and then we're going to go over it one last time. So similarly, let us take this for example. Here our temperature Tsat we had taken to be 25 degrees Celsius, right? And this was the corresponding Psat line. Now let us go to B12 and let us grab any value of pressure. Let's take 10 kilopascals of pressure. So this is the 10 kilopascal line, and the corresponding T is the Tsat, which from the table at 10 kilopascals we can see is 45.81 degrees Celsius. And also we can see the value of Vf at how many? At 10 kilopascal is 0.001010. Let us write that down. 0.001001, something like that, right? Not really relevant exact value right now. And Vg is 14.67355. Right. So now I think I will just move this a bit more down so that it's more clear. If our V is if our V is less than Vf, that means it must be lying in this region. And as we know, this region is a subcooled region. It also must mean our substance is subcooled. If our V is between Vf and Vg, that means it must be lying in this region. And we know that this is the saturated mixture region, which means our substance is also a saturated mixture. And lastly, if our V is greater than Vg, it means that our substance is lying in this region, and it is a superheated region, which means our substance must also be superheated. So this is probably the most comprehensive guide to identifying the phase of substance. I would highly recommend watching this video twice or even thrice to be able to understand what exactly is going on, right? So now we know how to identify in case of given P and specific volume, given T and specific volume. And we also know how to identify when both P and T are given, right? Now, let us move on to the last case. Using table, however, I don't have table A.2 in my PDF, so I will not be able to solve it with you here. Using table A.2, i.e. P crit and T crit. Remember what these were? These were the pressures and temperature at the critical point of the graph over here. Right. Let me just draw the diagram, and then you will automatically be able to understand what is going on. This is our critical point. This is our critical specific volume. Sorry, this is T. This is T crit. And this is our critical pressure line. Okay, so now if our pressure is less than our critical pressure, it means our line must be somewhere here. And if our T is greater than T crit, it means our line must be going like this. That means the intersection of these will be in the superheated region. Therefore, a substance is also superheated. However, if T is less than T crit, then we will have some trouble saying where it is, because it can be subcooled as well, it can be a mixture as well. So we will not be able to find out. So that case will never come. It will always be this case. And similarly, this concept can be translated into a PV diagram as well. So after all this, we will finally move to questions. Let me copy the question for you. These are the fair notes, right? The PDF, as always, will be available in the description. That's this. Yep. Okay, I have increased the size so we can see more clearly. Determine whether water at each of the following states is a compressed liquid or a subcooled liquid, a superheated vapor, or a mixture of saturated liquid and vapor. So a substance is water. Let us look at the first part. P equals to 10 megapascal. V equals to 0.002 meter cube per kg. 10 megapascal is 10,000 kilopascal. I'll just do this in pink. Yep. And yeah, so now we have been given P and we have been given V. So we will be drawing the TV diagram. Just a second. Yeah. So let us draw a 10,000 kilopascal line. Sorry, not T, P. And let us see what a saturation temperature is. Note that this is not required, but it is always helpful to find it out and write it down for later. So at 10,000 kilopascals, if we refer to table B.1.2 and we scroll down at 10,000 kilopascals, our saturation temperature is 311.06 degrees Celsius. Sorry. And now we will find out the values of Vf and Vg to compare the given V with. Okay, if we see the value of Vf, it is 0.001452. And similarly, when you see from your table B.1.2, let me write it here. It should read saturated water pressure entry. Saturated water pressure entry. Vg will come out to be 0.01803. Now clearly V lies between V and Vg. So V is somewhere on this line. That means V is somewhere in this region. And we know that this is the saturated mixture region. Therefore, water is in saturated mixture phase. If you do not understand, don't worry, there's a lot of questions in this tutorial. However, do feel free to go back and watch this specific question again. Let us go to part B. Given P is 1 megapascal and T is 195 degrees Celsius. So this is case 1. 1 megapascal is 1000 kilopascals. So we can do it using either of the methods. We can use the TV diagram or the PV diagram, right? So let us do it using the TV diagram first. TV. Can never draw this perfectly in one go. Anyways, so let us draw our given pressure line. So this is a constant pressure line. And let us find out the saturation temperature at 1000 kilopascals. Again, referring to table B.1.2, the saturation temperature at 1000 kilopascals should come out to be 179.91 degrees Celsius. However, our given pressure is somewhere over here, 195 degrees Celsius, and the point of intersection clearly lies in the superheated region. Therefore, water is in superheated phase. Now let's do it using method 2 just for the sake of verification that we do in fact get the same answer using PV diagram. PV, and this is now a constant temperature line. T equals to 195 degrees Celsius. For this, we will have to refer to table B11, and we can see that 195 degrees Celsius has the corresponding saturation pressure of 1397.8. So Psat is equal to 1397.8 kilopascals. However, our given pressure is only 1000 kilopascals, so it is below this Psat, and clearly it intersects one again in the superheated region. That verifies that water is in fact in superheated phase. Right, let's move on quickly to part C. It is similar to part A. We are given T at as 150 degrees Celsius and specific volume as 0.3 meter cube per kg. Let's draw the, as we are given T and V, here we were given P and V, and we drew the TV diagram. If we are given T and V, we will draw the PV diagram. This is T equals to 150 degrees Celsius. We will also be able to do it using a TV diagram, but it is generally useful to do it ulta. If T and V are given, draw the PV diagram. If P and V are given, draw the TV diagram. Okay, at 150 degrees Celsius, let us try to find out. At 150 degrees Celsius, first of all, we will note down a saturation pressure. Note that it is not strictly required, but it is a very good habit to develop for further problem solving. So at 150 degrees Celsius, it is 475.9 saturation pressure. The value of Vf will come out to be 0.001090, and the value of Vg will come out to be 0.39278. Again, we see that our V is somewhere over here, right? Because this is around 0.4 and our V is 0.3. So it is in this region. Therefore, water is a saturated mixture. Okay, moving swiftly on to part D. We have been given the pressure as 15 kilopascals and the temperature as 15 degrees Celsius. So this is again case 1. I'll do it using a TV diagram because we've already verified that using P and TV We have already verified that using either of the diagrams will give us the exact same answer, right? So this is a constant pressure line and it's 15 kilopascals. Now let us attempt to find out the saturation temperature at 15 kilopascals from table B12. At 15 kilopascals, the saturation temperature appears to be 53.97 degrees Celsius. However, a given temperature is below that, so it will lie somewhere here. And the intersection point indicates that it is a subcooled liquid. Okay, that concludes this question. Now let us move on to question number 2, which is for a different fluid. If it is for a different fluid, that means we will have to refer to a different table. However, all of the data is presented in the same format and in the same general formula we are use it to. I know it says problem 4. My order is a bit out of whack. So yeah, it doesn't really matter. We're trying to understand it conceptually. Because if you understand it conceptually, then you'll be able to solve any problem by yourself. I'm also aware that I talk quite fast. So yes, apologies for that. Feel free to watch this video in 0.75 or 0.5 if it's not weird, because I generally find that is quite weird for me, right? Okay, let's get back to this question. Let me increase the size. Till now, it is quite straightforward what we have to do. Write the data, find corresponding data and saturation stuff from table, and compare it. That's all we are doing. Okay, our substance is now R410A. I call this R410A. Okay, let us do part A. T is 50 degrees Celsius. And what is this? See, now they've not given us what this quantity is, so we'll have to figure out what it is by the units. Meter cube per kg is the unit of specific volume. So we can say that the specific volume has been given as 0.05 meter cube per kg. So now let us draw the diagram. This is a constant. Oh wait, again, as we are given T, we should draw the P diagram, and it will be exactly opposite of this, right? And this is our constant temperature line, which is 50 degrees Celsius. And now we have to find which table is for R410A. I think it will be quite down. Ammonia, and then I think we have methane, not sure, CO2. Yeah, table B.4 is for saturated R410A. Let us write that here. Yeah, never mind. Right. So at 50 degrees Celsius, our saturation pressure is some 3065 point something kilopascal. Our VF and VG. VF will come out to be 0.001103 and VG will come out to be 0.00707. Clearly, our V given is greater than Vg, which means it lies somewhere in this region, which is the superheated region, which implies is in superheated phase. Right. Moving on to part 2. I think this will be the last question that I'll be solving, because the rest of them you can solve yourself. I think I'll take one more at the critical uh, temperature pressure question, and then I think that concludes this tutorial, because after this it's all quite repetitive and I would leave some questions for you to practice as well. Also, I need to make the next video. Part B, we have pressure of 1 megapascal and a temperature of 20 degrees Celsius. 1 megapascal is 1000 kilopascal. Let's see. Now here, unlike water, we do not have both a pressure entry and a temperature entry. Table B4 has been given as a temperature entry. That means we are given the temperature, and corresponding to that we are given some pressure. In water it was both ways. We were given temperature and corresponding pressure, and we were given pressure and corresponding temperature. However, for all of the rest we will have only temperature and the corresponding PSAT. So what should we use is the question. Yeah, we will be using a TV diagram, as this is a constant pressure line. Oh no, we should use a PV diagram because we know the pressure to be constant. Sorry, we know the temperature value from the table. So this is a constant temperature line at 20 degrees Celsius, and at 20 degrees Celsius from B.4.1 we are able to see that the corresponding saturation pressure is 1444.2. However, our given pressure is lower at only 1000 kilopascals. Again, this falls in the superheated region, which means R410A is superheated. R stands for refrigerant. Superheated. Okay, moving swiftly on to part C. P equals to 0.1 megapascal. Again, no unit has been given. No quantity has been given. We're going to have to identify it via the units. A specific volume is given to be 0.1 meter cube per kilogram. 0.1 implies 100 kilopascals. And give me a second. Yeah, I hope you attempted to solve that. At 100 kilopascals, and a specific volume is given to be this. As we are given P, we will be drawing a TV diagram, and this is a 100 kilopascal line. Now we're gonna face some issue, because we know only the temperature and the corresponding pressure. We do not know at 100 kilopascal the temperature will be this or whatever. So what we can do is we can interpolate, or if the value is very very close from the table, we can use the next highest or next lowest value. For example, 100 is very close to 99, 100 is very close to 101. So, as table has a 101.3 kilopascal entry, we will be using that entry. At 101.3 kilopascals, our saturation temperature will come out to be minus 51 point something. Please note that the 101 kilopascal line will be slightly, ever so slightly above this, right? But we are disregarding that for the sake of convenience. Obviously, you can always linearly interpolate, but that is a topic for future discussion. So our Vf is approximately because we're not using exact values, we're not interpolating, we're using the 101 kilopascal values, 0.000741, and a Vg will come out to be 0.22418. Again, as Vf is less than Vg. So that means, remember, this point is Vf and this point is Vg. So it is in this region, which implies saturated mixture. Okay, part T, last part. T is negative 20 degrees Celsius and P is 200 kilopascals. As we know the values of temperature are more convenient to find, we will use a PV diagram. This is the negative 20 degrees Celsius line. I think it would be better to use a TV diagram, in fact. What did we do over here? Okay. PV diagram is correct because that's what we did above also. At negative 20 degrees Celsius, saturation pressure is 399.6 kilopascals. Come on. Yeah. And since it is lower, it is superheated. And now an obvious question arises, what happens when we try to use a TV diagram? Is it wrong? The answer is no, it is not wrong, but it is quite difficult to find the values from the table. So we will have to look for the value that is closest to 200 kilopascals, which appears to be 218.4 degrees Celsius. And this temperature is negative 35 degrees Celsius. And we are lying here. So, sorry, we are lying above. Negative 20 is greater, my bad. We are lying over here. Again, it is superheated. But please notice that while our temperature values in the table are given in multiples of 5 and a convenient multiple, the pressure values are only the corresponding saturation pressure values. So they're not very neat and they're not very constant, which is why we had to use an approximation of 218. So it is better to use whatever value is given to you very neatly, and that is the temperature value. Since we knew the temperature value, we were able to find the corresponding saturation pressure and compare it with the given pressure. Okay. Last question. The thing to note here is it is telling us to use table A.2, which is a critical pressure and temperature table. So let us just draw the diagram first thing here. Right, this was a critical point wala diagram that we drew above also. This is T crit. So now from the table we will be able to get the value of T crit as 304.8 Kelvin equals to 304.8 minus 273 equals to 31.8 degrees Celsius. Please take take note of the unit that is used in the tables, because in table A.4, or in fact in a lot of other tables, the units are often in kilojoule per kilogram, or in Kelvin per kilogram, or simply in Kelvin. So we have to convert all of these to degree Celsius and all of these to joule per kilogram, right? So taking note of the unit is very important, because if I had taken it to be 304.8 degrees Celsius, then obviously my answer would have changed completely, right? So T crit is 31.8 degrees Celsius, and this is the critical pressure line. So now a given temperature is higher, and a given critical pressure is lower. So real quick, P crit value is given to be 7380 kilopascal, a huge value, and P given is 0.4 into 10 to power 3, which is 400 kilopascals, which means a constant pressure line will be drawn somewhere below this critical pressure line, right? Because it is less. So let's just draw it anywhere. This is our 400 kilopascal line. And now our given temperature is 50 degrees Celsius. So means it is greater than T crit. It will be drawn above. So somewhere like this. Clearly we can see the intersection lies in the superheated region, right? Therefore CO2 is superheated. Okay, going on to part B, that we will also be solving in a similar manner. Let us quickly draw the diagram again. This is the most important diagram, guys. इसके बिना नहीं होता. So from the table, P crit comes out to be 550 kilopascals. I'm not opening the PDF because I do not have the pages in my PDF. However, in your table, you do have table A.2. So be sure to see it. Don't just copy what I'm doing, right? It comes out to be 220 kilopascals. And T crit comes out to be minus 146.8 degrees Celsius. And a given pressure, what is our given pressure? Oh, a given pressure is 220 kilopascals. Okay. P crit is in fact 3390 kilopascal. Yes, that makes more sense. So as our P given is less than P crit, it means it's drawn below the P crit line. Whatever. It's drawn somewhere like this. And a T given, which is I'm thinking 25 degrees Celsius, yes, is greater than T crit. We will draw it above the point and we will see it is again a superheated vapor. And last part, I want you to solve these questions once again, or I want you to solve them by yourself before the quizzes, before the compre, whichever is your next major exam, because it's very useful to solve tutorial questions. I always never recommend people to do the book of thermodynamics because it's quite tricky and the questions are not usually asked from there, right? So our final question is also solved in the exact same manner. I'm just gonna draw it this time around. I'm gonna explain it a lot. So again, it is coming out to be a superheated vapor. Let me just see if I have any more questions for you guys. Okay, so after this is a small theory lecture before we jump into the ideal gas equation, and before we jump into quality factor and compressibility factor and all of these things, right? So yeah, that will be it for this lecture. See you in the next one.